Alright, so this sixth video is going to focus on atom structure and history. We'll talk about the different tar particles, what they represent. I do not want you to stress too much about history. I am reviewing it with you on the first test. There may be a question or two, but history is definitely not an emphasis in this course. But you have had it before, so I just wanted to review the highlights with you. Alright, so protons, neutrons, and electrons are the particles that we're going to focus on within an atom. The protons and neutrons found on the nucleus. The electrons are found outside in the orbitals. Protons are positively charged, neutrons are neutral, electrons are negatively charged. Protons and neutrons have a similar mass, while electrons are much smaller, about 1/1000th the size of a proton or neutron. Protons help us find which element we have. Every element has a unique atomic number, and that's where the protons come from. Neutrons help us determine which isotope we have, which form of the element we have. They are combined with protons to give us mass number. I'm going to review atomic number and mass number with you on a separate slide. And then the electrons, along with the protons, help us distinguish between atoms and ions of the same element. Atoms will have the same number of protons as electrons, while ions will have a different number. So you see that below. When atoms are electrically neutral, it's because their protons and electrons are equivalent, while with ions you will have an unequal number of protons compared to electrons. If you happen to have more protons, you will be a cation because you will be a positive ion, and if you have more electrons, you will be an anion because you will have more negative charge and therefore be a negative ion. So isotopes can only exist within an element, which means they have to have the same number of protons. But if you have an isotope, you will have a different number of neutrons. So an example would be like carbon-12 and carbon-13. The number that comes after carbon is representing the mass number. Since the protons are the same, the only thing that must differ are your neutrons. And so just review the symbol that we've used previously. The X in the middle is representing your element symbol, which you can get off your periodic table. The Z is your atomic number, which is your number of protons. So if you look at the example in white, you'll see that magnesium has 12 for its Z value for both, since it's got the same number of protons. It's the same element. The mass number is A, and that is the combined protons and neutrons. So in the magnesium on the left side, you have 24 for the protons and neutrons. Since you had 12 protons, that means you would also have 12 neutrons. While on the magnesium ion on the right, you have a mass number of 26. So taking 12 away from 26, you get a neutron number of 14. So these two are isotopes because they are the same element, but they have different numbers of neutrons. And then the charge will be in the upper right-hand corner. If it is neutral, it could have a 0 there, or it could be left alone, which is what we see on the left. So that magnesium, the 24/12 magnesium, is a neutral atom, while the 26/12 magnesium 2 plus is a positively charged ion known as a cation. If it has a positive 2 charge and it started with 12 protons, it is short 2 electrons, therefore it would have 10 electrons. So we're going to do a few more examples with that hopefully will help clarify anything. First thing I'm telling you is that fluorine exists as an atom, and it has so many neutrons. So by the fact that we know it's fluorine and that we know it's an atom, we can find both its protons and its electrons. If you go and look at your periodic table, you're going to see that fluorine has an atomic number of 9, and therefore it has 9 protons. Because it's an atom, the protons and electrons must be equal, so it also has 9 electrons. And because it is an atom, also because you have the same number of protons and electrons, its charge would be 0. So to write the chemical symbol, I would put an F in the middle, and then the atomic number, the protons, is in the bottom left-hand corner, 9. The top left-hand number, the mass number, is your protons plus neutrons, 19. And there's no charge. You can either write it as a 0 or you can leave it as is. When you are writing an isotope name, you do want to specify what form of that element you have by including the mass number. And I've given you an example at the bottom, silver 108. So if I was going to write this particular substance as an isotope name, I would write it as fluorine-19. So our second example is an oxygen ion. You are told it has 9 neutrons and a charge of -2. By knowing that it's oxygen, I can go to the periodic table and find its protons, 8. It has a negative charge, which means it has more electrons than protons by 2. So if it started with 8 protons, it must have 10 electrons. From this information, I can write my symbol, O being the element, the atomic number being the protons in the bottom left-hand corner, 8. The top left-hand corner is your protons and neutrons, 8 plus 9 is 17. And then the charge for this one does need to be included, since it is an ion, minus 2. To write the isotope name, again I write oxygen dash the mass number, so oxygen 17. Part of the reason you keep being given neutrons is that you can't get that information from the periodic table. Just a reminder, that is a weighted average of all the particular forms, all the different isotopes of that particular element, and how often or how commonly they're found, the relative abundance of those isotopes. So for a specific isotope, you would have to be given information either in the form of the mass number or in the form of the neutrons to be able to find the other part. So in this next example, I'm not telling you the identity of the element by the name or by the protons, but I think I've given you enough information to be able to determine which element it is. You're told it has 47 neutrons, 36 electrons, and a charge of +1. Well, charge can help us determine protons because we know the number of electrons. We know that it's positively charged, which means it has to have one more proton than it has electrons. So therefore, it has 37 protons. By looking at our periodic table, we can identify what element has 37 protons. It's rubidium. And rubidium is acting as an ion in this particular example because it does have a charge. Rubidium's symbol is Rb. Its protons are its atomic number, 37, the bottom left-hand corner. The mass number is the sum of 37 plus 47, the protons and neutrons, 84. And the charge is the difference between your protons and electrons. We've already calculated that to be +1. Actually, that was given to you. That makes life a little bit easier. And now to write the name, I would write rubidium dash the mass number, 84. In our final example, I have silver 108. And I told you it has a charge of 0, which means silver is acting as an atom. I can go and look on the periodic table and find the number of protons, since I told you it was silver, and there are 47 of them. If it's neutral, it has to have the same number of electrons as it did protons, so that takes care of that column. And because I gave you the 108, that's the sum of the protons and the neutrons. If I know my protons, I can take the difference between them and calculate the number of neutrons, 61. So when I write my symbol, Ag, the 47 is in the bottom left-hand corner to represent the atomic number. I've already combined 47 and 61 to give 108, the mass number that's after the isotope's element, and so that would go in the top left-hand corner. And then because this did not have a charge, you could leave it as is, or you could put a 0 there. All right, one other thing we're going to review, I did just talk to you briefly about atomic mass, how that's a weighted average of the different forms of that element's isotopes that are present and how often we find them, their relative abundance. This is kind of like weighing grades. Certain classes will do things by points. Others will say that homework counts X%, quizzes count X%, things like that. And so that can kind of help you determine where your grade should fall based on your averages. And we can use the same type of logic to calculate atomic masses that we see on the periodic table if you're given the raw data. So in this particular example, we have 4 forms of chromium. We're told 50 chromium is present 4.35%, 52 chromium is present 83.79%, 53 chromium is present 9.50%, and 54 chromium is present 2.37%. And we want to calculate the average atomic mass of chromium in AMUs. An AMU is just atomic mass unit. It's just used to represent the unit in which those mass numbers are being represented. So I don't want you to get too worked up about that. I think on your summer assignment you may have units of U's, and so sometimes they'll just call it that. Not anything to get too worried about. Because the isotopes range from 50 to 54, our mass should fall somewhere in between them. But we don't just get to add those 4 masses together and divide by 4, because we see that the percentages vary quite drastically. We've got 52 chromium that's present almost 84% of the time, and we've got 54 chromium that's present only 2% of the time. So based on those relative percentages, I would expect the atomic mass for chromium to fall closer to 52, but because you have a range of 50 to 54, depending on how the others fall, they're going to contribute to the mass the 52 chromium isotope is adding to the mixture. So we may see a slight difference once we add them all together. It doesn't matter how many isotopes you have. You take each isotope's mass. You could be given an exact mass or just a mass number. You multiply it by its percentage and divide by 100. If you want to go ahead and just move your decimal with the percentage, that works as well. So in this particular example, I took the 50 AMU for the first isotope of chromium and multiplied it by its percentage and divided by 100. And I'm going to do the same thing for each of the other 3 isotopes. You have multiplication and addition taking place, so you need to make sure you take care of the multiplication operation first in terms of order of operations. So when I multiplied the 4 isotopes and their relative percentages together, I got these as their relative masses. I will allow you with the atomic masses just to round them to 2 decimal places. I will tell you that in the directions, so do not stress out about sig figs with this. Once you have each one's individual contribution to the average mass, you can add them together. And we see that indeed it was really close to 52. It is slightly above 52, and that's because of the contributions of the 50, 53, and 54 isotopes. So our next example, we have nitrogen has 2 naturally occurring isotopes. Nitrogen 14 has an exact mass, so this is like the mass number, 14.003074 U, while nitrogen 15 has an exact mass of 15.000108 U. And we want to know what the percent abundance is of nitrogen 14. So I've given you the exact masses of both isotopes that are naturally occurring, and I am asking you to find the percentage of one of them without giving you the percentage of the other. We do know that nitrogen 14 and nitrogen 15, when combined together, should add up to an abundance of 1. So if we let nitrogen 14, the one that we're trying to find, be X, nitrogen 15 should be the difference between 1 and X. So that's what you see in that first statement there. And then on the periodic table that was provided to you to use for this assignment, we know the average mass of nitrogen is 14.007, and I just kept the units consistent by making it U. So this time, rather than solving for the average mass, we're going to use the average mass and the exact masses of our 2 isotopes to find the abundance of one, and as a result, we should be able to find the abundance of the other if you had been asked. So since the average mass is equal to the sum of the 2 individual masses when accounting for their percent abundances, I'm going to take nitrogen's 14's mass and then multiply it by X, since that's the relative abundance of that particular isotope as we've defined it. And I'm going to add to it the mass of nitrogen 15 and its relative abundance, 1 minus X. Hopefully at this point you see that this is going to be an algebraic exercise. So I'm going to distribute the right side of my equation through. The first term does not change, but I do need to distribute that 15.000108 U through to both the 1 and the X. So that gives me my first term of the second part of the equation, and this gives me the second term of the second part of the equation. At this point, I see I have 2 terms that just have U's, and I have 2 terms that have both U's and X's. So I need to combine my like terms. So I'm going to subtract 15.00108 U from the left side of the equation and from the right. That leaves me with negative 0.993 U. And then I'm going to add together the 2 remaining terms, which gives me negative 0.997034 U times X. Keeping in mind X is what I'm solving for, because X is going to help me get the relative abundance of nitrogen 14. So to get X by itself, I'm going to divide negative 0.997034 U through on both sides of the equation. When I do that, I get that X is 0.996. That's the relative abundance of nitrogen-14. So to turn it into a percentage, I just multiply by 100, and that gives me 99.6%. So if nitrogen-14 is making up the majority of this mass, which kind of makes sense given that this mass is really, really close to 14, nitrogen-15 is the difference between that and 100, 0.4. The reason why I'm changing from 1 to 100 with percentages is that percentages come about by being multiplied by 100. Alright, and the last part we're going to talk about in this review is history. So we have our models going from solid sphere all the way up to quantum mechanical. Solid sphere was developed by Dalton. It was the one that was the first kind of thought process as to what was going on in the atom. Dalton did not believe there was anything smaller than the atom, and that excuse me, I was getting ready to sneeze, that there are no protons, neutrons, or electrons, that it is indivisible. We know that that is not the case, but Dalton's theory of the atom was the first attempt to try to describe what was happening and gave us kind of a starting place for the rest of the scientists and philosophers to come up with their explanations for what was happening inside the atom. So with plum pudding, that was developed by Thomson. He used that cathode ray tube experiment to determine that there were negative particles throughout the atom, and therefore to make it electrically neutral, there had to be positively charged matter that was balancing out those negative electrons. Rutherford came along a little bit later with the gold foil experiment and determined that there had to be a center of positive charge, that it wasn't spread throughout, that the negative electrons were outside of the nucleus, and that the rest of the atom was just empty space. Planetary was developed by Niels Bohr. This was the first to really describe the movement of the electrons, and he thought that they moved in fixed orbits outside of the nucleus. This worked great for hydrogen, but not so much for any element larger than nitrogen. So any element had more than one electron. And then finally we came into Heisenberg, Schrodinger, and de Broglie, and the quantum mechanical. You may have heard this called the electron cloud model, or the wave mechanical model. There we go. In which the electrons did not have to move in fixed orbits. They could move kind of in whatever pattern they needed to, and that they were generally localized to what's called orbitals, as opposed to the fixed orbits that we saw with Bohr's model. So some of the key contributions of the various scientists and philosophers that helped to lead to the development of these models. Democritus was the first philosopher, to come up with the idea of the atom that Aristotle shot down for several centuries. And then we just talked about Dalton, specifically for his theory, besides being indivisible. He said that every element has the same type of atoms, but if you are different elements, you have different types of atoms, that your compounds will always have the same relative amounts and kinds of atoms, and that you can't create or destroy them. And with the exception of being indivisible, and the fact that elements can have different forms of the same, different forms of atoms in the form of isotopes, the remaining three tenets to his theory still hold true today. Just talked to you about Thomson and Rutherford. Thomson discovered the electron. Rutherford discovered both the nucleus and the proton, and then they're responsible for their respective models. Bohr was the first scientist to describe the movement of the electrons in the orbits, and he said that the electrons could actually move between orbits using quantums of energy, which was discovered by Planck. So he was kind of gave him assist with his model. Then the three scientists that are responsible for the current model of the atom. Heisenberg said that you cannot say where an atom is and where it will be going, both its position and momentum simultaneously, kind of describing the fact that they don't necessarily have to move in set patterns. De Broglie said that particles can have properties of waves, and that waves can have properties of particles, again trying to describe the random motions that we see with those electrons. And then Schrodinger, and we'll spend a little bit more time on this later on in the year, described quantum numbers, which is just the general address for where we would find the electrons at in those orbitals. And then the remaining two gentlemen I want to talk to you about, Chadwick was responsible for the neutron, and Millikan, determined what the charge was of an electron using what's called an oil drop experiment. So hopefully this will help you get through this part of your review.